Okay, um, so I'm not showing this explicitly, but it can be shown again that the wave function, okay, this function which describes the shape in real space of the wave, takes on this form when you have this Gaussian distribution of wave number values of wave numbers, takes on this form. Again, you have a Gaussian um, envelope function, but now this is a Gaussian in real space. Okay, so it's x is the distance along the axis there, and then so this envelope modulates a cosine wave. Okay, since they're multiplying each other, um, which basically has the wiggles. So in addition to this, what you can show is that if you multiply that sigma x times sigma k, okay, for a Gaussian, you get a half. Okay, if you again, the sigmas characterize the width of the distribution in k, or the somehow some again hand wavy the size of your wave packet. Okay, and in analogy with what we discussed in the last lecture, these are uncertainties essentially. These provide when you have a spread in values, that means that if you make a measurement for that quantity, you have an uncertainty which is directly related to the spread in those values. Okay, so sigma x and sigma k represent a spread or an uncertainty, and if you multiply those two, then you get a half. Okay, so I'm not showing that explicitly, but it can be shown. And furthermore, this Gaussian wave packet is in fact the actually is the um, has the minimum joint uncertainty in x and k, meaning that the product of sigma x times sigma k is equals a half, and that's the smallest that it can be. So any other form for a sub k, any other distribution of wave number values, any other one, will yield a value sigma x sigma k greater than a half. Okay, so again, the Gaussian is somehow the minimum wave packet. It doesn't mean that it's the minimum in space, because you can make wave packets that are narrower, that have a narrower distribution in real space, but that means that they're going to have a wider distribution in k space, in wave number space, and the product of the two is going to be bigger than a half. Okay, just to check the units here, if the units of sigma x are just, this has to be unitless, so the units of sigma x have to be spatial dimensions. Okay, so they're units of length, and the units of sigma k, okay, have to be in units of k, and since k is 2 pi over lambda, okay, then you have that sigma k is also in units of 1 over length. So when you multiply sigma x times sigma k, you indeed get something which is dimensionless, as I'm showing here. So there's no units on sigma x sigma k. It's a unit. It's a dimensionless number. Okay, so now we've basically done this for the spatial part of the wave function. That is, we've basically frozen time, and I've sketched what happens here. The same thing can be done for the time component, for the temporal component. If you let time run but you freeze space, then you can do a similar analysis in which you'll find is the same, basically the analogous relationship, that the uncertainty in time times the uncertainty in the frequency, the angular frequency omega, is greater than or equal to a half. Okay, so now we have these two uncertainty relationships, very analogous to the ones that we got for two arbitrary harmonic waves in the previous lecture, except for now we're talking about Gaussian wave packets, and so this provides a lower limit on the on the product of the two uncertainties. Now, again, we want to consider. We're talking here. We're obviously building towards a describing wave packets of actual particles, and so we want to actually plug in Broglie's relationships to find out what this means for actual particles, the momentum and energy of particles.